Toplanan ve geri dönüştürülen boş plastik şişe, kullanışlı şık bir çantaya dönüştürülebiliyor. Böylece plastik atık yeni ve değerli bir ürün olabiliyor. PAGEV, plastik sektörünün birleştirici gücü. Toplanan ve geri dönüştürülen boş plastik şişe, sportif bir tişörte dönüşebiliyor. Böylece geri dönüştürülen plastik atık yeni ve değerli bir ürün olabiliyor. PAGEV, plastik sektörünün birleştirici gücü.
Well, we will finish the workshop with Extrusion Dye Design. First, I would like to start with some general principles, and then I will take on the most common dyes, that is flat, coat hanger type dyes, spiral dyes, co-extrusion, and profile dyes to discuss. So these are the most common dyes. Well, you really have to be careful about what to look for with extrusion dyes. The most important, and I repeat, the most important subject is balancing, flow balancing. Right. What you want to do is, let us say, you want to produce a product like this, a sheet, thick, like this. So the thickness must be the same everywhere. But you're probably going to have an extruder. You're going to have an extruder feeding this polymer like that. And why would the polymer would prefer to go right down the center and not go to the side? So it is a very difficult subject. So flow balancing is the most important thing. And I'll show you how it is done. Then we have to be careful about a reasonable pressure drop. I say reasonable. You may want to say, well, we should try to have the lowest pressure drop, and less energy. But it's not always a very good thing. You want some pressure drop to have a nice extrudate coming out. You certainly don't want to have any hot spots, which you would avoid viscous dissipation, any flow stagnation, right? If your flow is stagnating, and problems relating to dye buildup. You would like also to delay as much as possible the onset of melt fracture, shark skin, weld lines. I'll talk about weld lines. And again, the residence time, how long the residence time, average residence time, local, so forth. Flow balancing. What is flow balancing? Take a look at this. We have a dye, as you see, in the central portion is 10% thicker, right? Well, let's calculate, if I put the same pressure in the back, how much I'm going to get. Well, we'll see. I use very simple equations, and I calculate. These equations are in your lecture notes, and I calculate simply that if I have a Newtonian fluid for that 10% thicker gap, wider gap, I end up with 21% faster average flow. You will mess things up, like, 10% will give you, if I have a non-Newtonian fluid, like, and I characterize the non-Newtonian fluid with the N factor, which gives you the shear thinning. And the shear thinning is 0.33. In this case, the velocity will be 46% faster, which means that the more shear thinning the material is, the more the imbalance. Now, this has some implications, because if you have designed a die that was working well for a material, or acceptably well, you could be happy with it. And then you put a more shear thinning material, and it doesn't. You know, think about this correlation. The shear thinning effect on flow balancing. This is a problem. Occasionally, I see it because people will tell me, oh, I was extruded this polymer, I had no trouble. I have a new one. You know, same die, same extruder. So this is one problem to consider. So we want even uniform flow for sheet, film, profile, pipe, etc. And you know, the smaller the n, the greater the tendency for flow imbalance. Something to remember. So the first die we're going to take is flat dies. And we use them for film or sheet. Now, the terminology, what is film, what is sheet, is really on the thickness. Sheet is considered a film that is thicker than 0.25 millimeters. This is considered sheet, you know, just terminology. You know, that's the official terminology and nothing more than that. Flow channel design, I have both a sketch and a mechanical design, and this die was designed and built by a co-author of mine. He has a company in Austria, and we wrote a chapter together on flat die design, but you cannot see very much. Well, it has to be good quality and all that. But here is this story. You see, from the extruder down, we bring the polymer right here, and of course the polymer would rather travel straight through, right? Rather than go all the way there to produce a sheet or film of even thickness. So what do I have to do? Here I'm going to put some obstacles. Here I'm going to obstruct the flow so that to direct it to that way. And in fact, I have an actual die. This was a die that was designed and built by Cloran in the United States. And you see, like, this is the feed section. This is what we call the manifold, which is a distributor. And you see we have a large gap over there. Then we have a long resistance here, but the resistance, of course, is reduced. And sort of also the manifold is reduced, so that gently, and then we have another manifold over there, and eventually we have the die lips. To do that, you do require a two-dimensional flow software. We have such a software, and we have designed, or our customers have designed, hundreds of dies. You know, that one is. The idea is to really, it's a trial and error, really, on the computer screen. Like, I remember, well, I've sold the package to several companies, but I got a lot of experience when a customer said, he would like to come over, didn't want to buy the package, but he want to design just one die, and like that, and he was very experienced. He had designed other dies pretty much on experience, and then he would tell me, okay, I would like this to be that long, and this gap, and this one, and whatever. And it took us, if I remember correctly, it was a graduate student of mine that was working on the project. I think it took us 52 runs to do it. Like, and he was experienced. Well, somebody more experienced could probably require about 30 to 40. So you give it, you check, and what you'd like to do is, at the end, the software predicts the local velocity coming out. So you have to adjust the packages in such a way so that you have even material coming out. You check the velocity of the outflow. So that's the trick. And it's difficult to do. It's really trial and error. I remember before I sold the software to a company in the United States, somebody asked them, I said, how do you guys design the die? And he said, well, like this, you know, which we're not happy, and then they purchased the package now. Well, with a lot of experience, but experience is the best teacher, they say, but the tuition fees are very expensive. Like I've seen it, somebody designed in my area, a big die, was heavy, it was a few tons. Then after he designed, after it was built, he said, can you fix it now? It was not fixed. It was bad, I tell you. It was bad, and it cost him a lot of money, and nothing came out of it, you know. And, now, if you want to learn more, I have written a chapter with my co-workers, Nicholas, and Tanifuji is works for a Japanese company, is a computer specialist, and Peter Müller is the guy that designed and built the die. He works in Austria, but I have just learned his company was sold to, I'm not sure to whom, but he was just, by? Oh, Reifenhäuser, you are right, absolutely right, Reifenhäuser, yes. He works for, the company was sold to Reifenhäuser, that's right, yeah. But I have a full chapter, which is downloadable from ResearchGate. If you go to ResearchGate, you can put my name, you can download this chapter easily. And I have a lot of details in that one. Now, spiral dies. Spiral dies, more interesting. There's much more. You know, it's a bigger business than the flat die business. And we'll spend a little bit more time on blown film production. Essentially, in blown film production, you really have to worry more than just the die, all right? Okay, the extruder would deliver what it can deliver to the die, and right now, of course, we have to have also even thickness around it. I'll tell you later that we can tolerate perhaps 5% thickness variation. Well, somebody told me they tolerate up to 8%. I'm more for the 5% because you create a lot of problems downstream. So the purpose of the die is really, the first job is to develop a tubular film of equal thickness, as equal as possible, which is not easy. And then you have other things, cooling, because the output limitation is really determined by the ability to cool down. Usually it is not shark skin. Like frequently, when we do work in universities for shark skin and melt fracture, we always say that shark skin is very important because it imposes a limitation and blown film, and well, with the addition of fluorocarbon polymers, you postpone it to higher output rates. But the problem that you have is cooling. And you will see that I will tell you a few things about external cooling. And also the latest thing is that you have internal bubble cooling, like you have air jets from the inside, also from the outside, right? To increase cooling capacity and achieve higher output rates. Now, what I say here is what I like. So the polymer would come from the extruder. There would be melt pipes right here to bring it to this, what we refer to as the port. You know, this is the port, the entry. And of course, it will go around, and another port over there, another port. So it will go around, and you know, the designer will design how many times, how much around the mandrel the spirals will go, all right? And you'll see the implications of that. And of course, some polymer is escaping between the spiral and the body. You see, like there's flow along the spiral and also between the spiral and the body. So this is a complicated flow field. It's really, strictly speaking, is a 3D flow field, which is difficult to analyze. But we'll see what we do. Cooling. As I said, cooling is originally was just a single air ring. You know, like that, you blow air, you cool. Well, now there are dual air rings. I have seen up to quadruple air rings. All right? Up to quadruple air rings. At least I know of one company that they tell me they use it, they do better cooling. And what the problem is the following, which you will see with a simulation, a computer simulation that we have. This is a computer simulation, and you will see how the air ring is structured. Okay? Now, you have this top part, which you can, normally you just turn it around and you move it up and down, which means that you can open up or close, and the air is moving through. And in this case, when I have the high position, this is how the air is distributed around the bubble. Now, in another case, because I have somehow changed the flow paths for the air, I have two phenomena. First of all, the jet, it comes out and wants to stick to this one. It comes out, then it sticks to the other. This phenomenon of having a jet attached to a surface. Now, you can demonstrate it in the kitchen sink in a hotel. You know, let the water come out, put your hand next to it, the water jet will come and stick to it. This is a very important phenomenon because locally, you see, heat transfer in this case and in this case is not the same. You see, the heat transfer is going to be slow or fast. It would depend on the local heat transfer phenomena, the local heat transfer coefficient. And in the work that I had done with a PhD student, we have actually determined the local heat transfer coefficients. And the local heat transfer coefficients, they're different in the left-hand side and the right-hand side, right? So the heat transfer coefficients determine whether the crystallized that you're going to be forming are going to be large or small. And this will affect the final properties of the film that you're going to be producing. Okay? And of course, you can add inside. We have done that work as well, this part on extrusion dye design is not included in the book that you have. It will be, because it's a preliminary edition, but it will be included in the next edition, which will come out around the end of this year. And I'll be sending it to you. I'll be getting the emails of all of you from Decon or PAGEV, and I'll send you a copy of the new book. We'll have also inside what happens with internal bubble cooling. Normally, internal bubble cooling, even if it's retrofitted, you can increase according to the size, if it's small, large, and so forth. Probably you can increase output rate by at least 20%. Maybe you can go as high as 30%. Same thing, everything, you just install IBC, internal bubble cooling. So it helps. So, and I say it, how fast you cool, and also whether the product that you're producing has the right properties, and the right properties are determined by a lot of factors, including the size of the crystals that you have. The frequent problems that people have is either shark skin, or generally if you're producing a transparent film, you may have poor optical quality. The opticals are good, I've seen many of them. And I'll give you a real problem. It was from a customer not too far from my university. And he called me up. He knew about my work and research and courses that I give. And he said, I've got a problem with shark skin, melt fracture. He said, shark skin melt fracture, and he was fixed to that. I said, well, I'll check this to see what is actually happening. And at that time, at McMaster was a student of mine who is, in fact, arriving tonight. It's Velichko Christoph. He's arriving tonight. He's working at Borealis now. He was a graduate student at the time, and I said, okay, let's see those guys. Let's check their flow curve. Like we measured, again, using capillary viscometer. We measure the customer's results and now, checked it against our results, and then see if and when we get smooth or shark-skinned kind of polymer. So we noticed that it happens at about 200. It was a bit less than 200. But when I checked the quality of the extrudeds, and the output, and I concluded that what they have, they were telling me they had shark skin, but when I checked the shear rate, shear stress, I said, no, it's not shark skin. And, but we did have good measurements, which you could trust, and we could do a computer simulation. So shear rate and shear stress were lower than for the onset of shark skin on the die lip wall of the blown film spiral die. So it was not shark skin, it was something else, probably related to the die, so we carry out an analysis of the die. Well, at that time we had a software like that. What we're checking essentially in the analysis of the die, this is a fancy picture but doesn't tell you very much. What we were searching is local shear rate at the wall. Never mind the beautiful picture. We determined the local shear rate, and this is what we found. Take a look at it. This tells us the flow. This is the spiral channel which has been unwound. You know, we took the spiral channel and we unwound it, right? And this is, and then in our software, we can tell how much flow goes in this direction. And of course, there's something comes out. And we notice that in the beginning, there's a lot of flow going, and then it drops, it drops, it drops. And the last yellow section, 20% of the spiral, there is no flow in a direction. Well, that means we have a stagnant layer in there. Okay? It's a so this is what I'm saying again. With the help of SpiralCAD software, we discovered that 20% of the spiral, there is no flow. And in industry, the word is, immediately when I saw that, I said, we're going to have trouble. And we take a look at the local shear rate. In industry, the general norm is to have software that is larger than 10 reciprocal seconds. How was this established? By experience. It's something that no university professor is doing research on. I'm the only university professor probably that talks about it. But everybody in the blown fill industry knows about it. Nobody's going to accept a die that has, under the production conditions, shear rate that is less than 10 reciprocal seconds. It might be lower. In this case, the designers and builders, manufacturers of the die had actually taken my course that I give. And I submitted a report and so forth. And then they said, I told them, I said, you can use mine. I told my customer, use my name. I submitted the report. And I say that the wall shear rate at the end of those spirals that you have seen is very, very low, predicted very close to zero. And you see that yellow part, it is very, very low, which means that we have a stagnant flow layer and it remains there, and the polymer gets degraded. For example, if you have HDP under high temperature conditions and long residence time, long residence because it's stagnant. HDP is here, it just gets cross-linked. So it does not produce shark skin on the surface, but inside the film, it has a cross-linked material. And this cross-linked material gives you some kind of poor optical properties. And this is what bothered my customer. And most of the problems that I have been getting over the years is of this nature. The dye has a region of rather low shear rate and gives you these problems. In fact, the company, well-known company, I will not mention the name, in blown film lines, they had taken my course, they knew about it, and they designed a new dye with their own software. They sent it to me, I checked it. Well, it was not perfect. The new dye, it is difficult to get it perfect. I'm recommending no less than 10 reciprocal seconds. Some people may say 8 is good enough, somebody else may say 7 is good enough. Well, in their case, it was about 5 or 6. So the customer, I told my customer, he accepted it, and I asked after that, I said, how does it run? And in his way of expressing the outcome, he said, well, it's not perfect, but it's 50% better, you know. So he was happy with it. He was doing a better product, and so that was the problem solved. Another problem that we have is co-extrusion. And co-extrusion is a very big business. Like most of the blown film dyes that I see, I hardly see any monolayer extrusion, to tell you the truth. Every time anybody, in a way I don't, you see, I work as a consultant, and I only see people, they have problems. If they don't have any problems, I never see them. But most of the blown film lines that I see, they're multi-layer. Very frequently, they're 3 layers. They go up to 9, frequently 11 layers. And they do exhibit certain very specific problems. I'll tell you about some of them. Now, the first problem is layer-to-layer non-uniformity. You see, you co-extrude two polymers, they flow together in a channel. And as you will see, the less viscous polymer is trying to encapsulate the more viscous one. Okay? And this is natural tendency. Nature wants to limit the expenditure of energy. So if you put the more viscous on the wall, as you see over there, you see, this is an actual experiment. I think they were produced by Jim White, if I'm not mistaken, the founder of PPS. And you have, you put the 2 layers together, and then the less viscous white layer is trying to encapsulate the more viscous one. Why? Because if I have at the wall, if I have a polymer of lower viscosity, I have lower pressure drop lower energy expenditure. Okay? Now, the situation, of course, becomes much more complicated if I have co-extrusion inside a flat die. In this case, we really have to be careful how to distribute the polymer from here, because you're going to have a layer. Is this layer going to, most likely what you're going to get is something like that. And it does require some trial and error. Like for those dyes, my software has not been terribly successful because it's very difficult to decide how, what thickness we put one and the other. But it does require some experience, and the way we do it normally is by what we call feed block profiling. What is feed block profiling? You see, if you put, let's say you have a rectangular die like this, and the black polymer is more viscous than the white one. So when they travel together in the channel, then the less viscous black polymer is trying to encapsulate the more viscous one. So what do? We profile the feed block, which feeds from the extruder the polymer to the die. So we put this thing here, right? So we anticipate the result, right? And then if we put that one here, put more, so at the end we may end up there. But this one does require some trial and error and experience. With computer simulation, we tried to do it, but we were not that successful. Like, I don't have a software that solves the problem. It's not that easy. Again, you see other configurations like this, or if you have 3 layers, you put them just parallel together, you're going to get something like that, because the less viscous gray or black polymer, whatever it is, tries to encapsulate the one. So we do something like that in the profile, so we end up something like that. So this is called the feed block profiling. Now, another problem is what we call interfacial instability. Interfacial instability, it gives you poor optical properties, but it is not shark skin. Like, if you had shark skin, you would have similar problems. This is not shark skin. There is nothing on the outside surfaces of the film. It's at the interface between 2 layers of polymer. All right? So that's the first distinction. So that in this case, there is a bad film and there is a good film, and both of them, if you put the film on the top of a paper, you have written these words over there, put it on top, you can read it. However, if you remove it just 1 inch, 2.5 centimeters, there you see. You see, if you have you see, with a good film, you can still read film 2.5 centimeters from the paper. But a poor film, nothing can be read. You see, there's an enormous difference in quality between the good and the bad polymer, or the good and the bad film. So it's an interfacial instability. What we have found out over the years that this is related to interfacial shear stress. The magic number, I'm not sure if I have written it here. Oh, yes. Yeah. The magic number is that the stress at the interface, if it is below 60 kilopascal, I have no problems. It may go up to, of course, those numbers are not, as we say in colloquial English, is not cast in stone. I mean, we say 60, maybe it can go to 70, can go perhaps to 90 kilopascals. But if it is, let us say, above 90 kilopascals at the interface, I guarantee that you are going to have interfacial instability. So that if you want to avoid it, this interfacial instability, you have to somehow lower the shear stress at the interface. How do you do it? All right? Well, there are a few things. They're very simple. Decrease the total output. Well, you may not like it, because decreasing the total output means, less para, the money. You may not want to do that. So this one, it's effective, it works. If you try it, you solve the problem, you lose money. One thing is to increase the skin layer thickness. For this one, I may have to go to the blackboard over there. Do you have any pen? Is there a pen? Do you have a pen? There's a pen. Okay, thank you. So what we have is wall. The wall is right there. Then the shear stress would vary linearly. And let us say here is 0. And here is the interface. All right? So this is the shear stress is max. So one thing that you can do is if you have the interface right here, right? You're going to get a value, let us say, whatever it might be, let us say if it's 80, right? And 80 kilopascals is going to give me interfacial instability, the problem that you have seen. But what I can do, I can perhaps move this one a bit down. Well, here is lower. We can go to 70 or 60 and we solve the problem. You see, that's one of the tricks that it is done in order to reduce the shear stress to a lower value. Okay, thank you. So take the interfacial layer away from the wall. That means you reduce the shear stress at that position. You avoid the onset of interfacial instability. Another thing is you might decrease the viscosity of the skin layer, right? Again, the shear stress will go. And you may want to increase the die gap. Again, you lower the overall shear stress. And I have a warning that I say this is a popular remedy that does not work. Now, some people think, well, I have interfacial instability because I have different polymers. They have different viscosities. Well, how about matching the viscosities of layer 1, layer 2, layer 3? No. Actually, we have done experiments with blown film. Same polymer coming from different extruders. When they merge, they do exhibit interfacial instability. So matching viscosity does not work. What you do is lower the interfacial shear stress. So that's why I put this warning at the end. Now, if you want to read more about this subject, there's quite a bit about it. We talk about it in our chapters, which are available. There is a book on multi-layer flexible packaging, and there's a very good film extrusion manual there. These are all good references. If multi-layer co-extrusion is a problem, and of course you have to consider all the other possibilities because as with shark skin or any other problem, customers or engineers, they have fixed ideas of what this is or what this happens. And I had one of them that was from Luxembourg. Was somebody had taken actually the course, and he said, okay, now I know how to. So he called me up and he said he had interfacial instability. He had 9 layers. And we checked. Well, I checked all the interfacial shear stresses, and the interfacial shear stresses were lower, were not high enough to cause interfacial instability. So I said, well, it's got to be somewhere else. And after studying the problem further, he determined that the problem was generated in the extruder, the stuff that I told you about Moffat Endies. It would generated, gels were generated inside the extruder, and these gels, small particles, were going into the film, and the person thought there was interfacial instability. So it's important to keep in mind that interfacial instability is a problem. It can be solved, but don't forget all the other things that we talked about. Profile dies are the toughest of them all. Designing of a profile die is more of an art than a science. The problem that you have is really balancing the flow, and I give you a challenging problem, a keyhole die. So you're coming from the extruder right here, and you have a parallel section, as you can see, and then you have a round channel. And if you push the polymer right through, you're going to end up with a very thick, round extrudate and a very thin, flat extrudate like this. You see? Well, what can you do? This picture pretty much tells it how it is. In the back of it, we are going to put more resistance in the back of the wide channel, like the round portion is wider. So the polymer has a preference to go through this section right here rather than this rather narrow gap. So you can put more resistance in the back. Well, I mean, this is one of the remedies, but you could perhaps open this, maybe perhaps make it converging. There are different remedies, you know, how you can, you know, balance the dye. Generally, it's rather complicated, and even computer software is not, well, it's helpful, but it is not 100% the solution. So that's what you have to be aware. Like computer software can help, but it will not be 100% the solution. I do remember one of my former students went to a company nearby, and they were making automotive parts. And you know pretty well what happens, eh? And it is tough. He was telling me that some dyes, they had to be retried 100 times. Do you agree, Jakub? You agree? 100 times. And you tried, you run it, and the workers were very happy because they had to work Saturday and Sunday and getting overtime pay. And then my student goes over. He had my software, which we call it Profile CAD, that helps you design it, which was a two-dimensional software, and then bought the Polyflow software, which everyone knows about it. And then the rumor was spread in the company that this young guy now is going to design on the computer the dyes, and all those venerable workers would lose their weekend pay and extra pay, 50% or 100% if it's a Sunday, more and so forth. Well, they found out that this was not the case. Well, I mean, he could accelerate the process, perhaps reduce the number of trial and errors on the shop floor, but the situation remained the same in the sense that they had to do a lot of trial and errors. From my own software, the best information I got from a company in Colombia, South America. It was a small outfit, but they were very smart people there. And I sold them a software package, and they started designing, and it was rather simple designs, whereas my student was working in very complicated automotive parts. And then I asked them, I said, well, how are you doing, you guys? You know, are you producing better dyes, faster, whatever? He said, we used to do 10 to 12 simulations, trial and errors, before they bought the software. After the software, they were doing the trial and error on the computer screen, you know, what should be the resistance and so forth. And they were able to reduce perhaps to 10, reduced it to about 5 or 6, 40 to 50% reduction in time. And this is what I expect. It's It's a very complicated situation. There are a couple of small companies, they sell software, fully 3D software. However, the situation is difficult. Even the design of a complicated profile die is really taxing the computer itself. You need a lot of time and effort to do the simulations. So it is not a clear-cut solution, you know, how to do it. So trial and error is eventually required for these kinds of dies. So you can find, I have some stuff on profile dies, and these are the key papers you can take a look at. Now for pipe dies, the big trouble is with what kind of a die you're going to use. Are you going to be using spider legs? The Pipe Life people. Pipe Life? Who is the Pipe Life guy? Okay. What are you using? Are you using spider legs, or are you using spiral dies? Spider legs. You have spider legs, that is. How do you're making a pipe, right?
Sorry?
You're making a pipe.
Yes.
Well, what's the diameter of a pipe?
As a die, I think I'm 2 months. I have been there. It has been 2 months.
Yeah.
I think the regular type die they are using.
Okay, regular type die means that you are supporting the central portion to the outside by some kind of a support, right? Which means that you have spider legs. The shape will be something like that I show, and of course the polymer flows behind. The polymer flows behind it. You form a weld line, and this is a line of mechanical weakness because it's very difficult for the polymers to penetrate, and bonding is poor, and it can be avoided. You can avoid them by having better melt homogeneity. Higher temperature would work. Higher pressure perhaps, and special spider leg design. Now, this is special spider leg design. Well, the polymer comes right here, but you see, you split the weld line. You split one there and one there. And that sort of, by splitting it in the back, you create a situation that improves the mechanical properties. And I'll show you, well, here I am. Some of those dies are pretty big, as you can see. And in this case, is the production of a corrugated pipe. In fact, machinery of this kind is available in Turkey. I know for sure it's available in Gaziantep. My client has sold to Gaziantep, a couple of places there. They have sold equipment for corrugated pipe design. The way you do the corrugated pipe is by having, normally it's 2 layers. So you have a die that you extrude 1 layer of a pipe, on top of it another layer, and you have a large number of molds that keep moving. When I say large number, the molds can be 100. One is coming like you know, a tank, you know, yes, sort of, so they come together and they form these corrugations, and corrugated pipes of course, are like this, and the corrugated pipes, they increase the stiffness, and they used in sewage and stormwater applications. And at least in Gaziantep, in Turkey, there's a big, I'm not sure what sort of construction is going on down there, but there's quite a big of use. And these pipes are subject to the test that I have talked to you about. And there's a very flattening test, and depending on the situation, you will see that if I apply a load like this, I'm compressing on the top, I'm extending on the bottom, and of course you're going to have something like that, and it sort of it breaks. And this flattening test is a tough one, you know, like it has to go, I think, 40%. They require 40% flattening test without damage. It has to come back, you know, and it's a tough one. So the design and all the stuff that I told you about the polymer, about the extruder, about everything else has to be taken into consideration. Crack growth in pipes, of course, I did mention an example before. Environmental stress cracking resistance, those things are important and should be taken into consideration. In the corrugated pipe business, you do add a lot of calcium carbonate. Reason is, of course, that you reduce the cost. The stiffness goes up, all right? So you get better modulus, but ductility drops, so that you have a trade-off. I mean, do you want high stiffness modulus, or you would like to have ductility? It depends on the application. And it must pass a very strict test. I think this is the last kind of dye that I'll be talking about, is wire coating, in which an extruder supplies sort of the wire is moving, and as it moves along, it drags the polymer with it. In some cases, it is possible to have some kind of recirculation. Recirculation should normally be avoided, but it might be there, and if it is there, you better know about it. One thing that is rather different from everything else that you've heard from me in this workshop is with wire dyes, when I check actual installations, the shear rates are out of this world, you know, they're over 1 million, you know, that's the way they operate. Like 4 million, last one I checked was 4 million shear rate. I'm not really sure, because they're successful, and you cannot really argue with success. They are pretty successful, but I don't really know how they work without having problems of instability like shark skin melt fracture. Some people have tossed the idea, have toyed with the idea that there's a second region of stability, like if you extrude too fast, you have wall slip, and many of the problems that we talked about do not really occur. I do not really know very much about it. I recommend these books. on various aspects of extrusion, screw extrusion, and flow through dies and whatever. But for where dies, there's Evan Michulis, you've published a paper, right? Anything that you can remember?
Everything was right.
Everything was right. The simulation was right. But it works, you know, at very, very high shear rates. And to me, is a bit of a mystery if it is indeed a second region of stability. And with this slide, I will conclude my presentation. I have a number of things, and I'd like to tell you that in the book, the same material is presented. I have not included the section on dye design is currently being written. My co-author is writing this chapter right now. I'll be going over it, probably have it in a couple of months, the chapter on extrusion dyes, and I will add a chapter on twin screw extruders, and also a chapter on 3D printing, because extrusion also is used in 3D printing, because you have a what they call fused filament deposition, because all the extruded problems, all the dyes, everything is the same. Melt fractures, shark skin, vortices, everything is there. And so we'd like it to give it special emphasis in that area, with some additional problems relating to when you deposit the layer on a surface, what sort of product are you going to get, and what would the properties be? Because you have injection molding, you have very, very high pressures, and you compress the material, you improve the properties. In extrusion, you have good properties, but in the case of additive manufacturing, you lay one layer against another, and would the properties be acceptable? And with that, I conclude my talk, and I thank you for your attendance.
We would like to thank you
Okay.
on behalf of PAGEV Administration for the memory of today. Oh, wow. Yeah.
Thank you very much. Teşekkürler.